today we would be talking in some more detail on synthesis. Now, if you recall what we had discussed in our earlier classes, we had looked at the language Verilog as a tool for modeling, as a tool for specifying behavior, specifying structural aspects of a design, specify the test benches using which we can simulate our specification and we can obtain a validation of our specification and design. Now, after we have specified a behavior of a design, the next natural step is to carry out a synthesis. Synthesis is essentially a detailing out of the design. So, first let us try to understand what are the scopes of this synthesis process. Now, in order to do that, we first look at the so called Y diagram again, which we had seen earlier. Now, in this Y diagram, if you recall, there are three dimensions or axes to a design. The same design we can specify with respect to its behavior, with respect to its structure, where, well, at this level the design would consist of a block diagram, some cells and their interconnections, and finally the implementation level or the physical level. Now, in terms of the Y diagram, you can assume that there are several concentric circles as we have shown out here, and as we move away from the center of this Y towards outside, the design becomes more and more abstract. So, when we are at the outer layer of these circles, we are at a very abstract level, may it be behavior, structure or physical. But as we go towards the inner side of this Y, the design becomes more and more detailed. Well, we'll explain this with the help of an example, but before that, let us try to see that how the transformation from behavior to structure to physical takes place. So, let us look at a diagram like this. Well, this is the same Y diagram which shows behavior, structural and physical views. Now, the behavior level, if you recall, this specifies the behavior of the circuit or the system without explaining how this behavior has to be implemented or realized. Now, herein comes the process of synthesis. So, when suppose we have a given behavioral description out here. Now, when we carry out synthesis, we translate this behavioral description into the corresponding structural description. This is the process of synthesis. Now, in the structural description, our basic building blocks will be some components. Now, the components may be cells from the libraries, it can be gates, it can be transistors, it can be anything depending on the level we are looking at. Now, this translation from behavior to structure is also sometimes called front end design. So, when we talk about front end design or front end CAD tools, we are essentially talking about the translation from behavior to structural. Well, now once we have this structural view of a design, the next step is to map it into the implementation level. For example, if it is an interconnection of transistors, so that will have to be mapped into a corresponding level which will mean the layout on the floor of the silicon. This process from structural to physical design transformation is called physical design, and sometimes this process of translation is also known as back-end design or back-end CAD tools. Okay. So, this diagram will give you an overall idea that what we are trying to do. First, we will be using the front-end CAD tools for synthesis. Next, we will be using the back-end tools for physical design. So, once this entire cycle is complete, our physical realization or implementation is ready. Okay. Now, let us see, we had said that on this Y diagram we can superimpose the circles, and as we go towards the outside of this Y, the design becomes more abstract. So, let us try to understand what this means. Okay. So, we start with a circle which is the most abstract design that we can think of. Well, in terms of the behavior, at the most abstract level, a design can be specified by simply specifying the algorithm, or if it is a system level design, you can also specify the flowchart. So, algorithm or flowchart is a very high level kind of a design specification. So, when we synthesize an algorithm or a flowchart, at the corresponding structural level, we will have some kind of a block diagram. We will have some basic building blocks and their interconnections. Now, these basic building blocks at the level of algorithm or flowchart will be something like processors, memories, buses, other IO interface units, etc. So, as you can see that the basic building blocks are very high level modules. So, at this abstract level, we are more concerned with a block diagram kind of a design, how these high level blocks are interconnected, rather than going into the details of it. And similarly, when we talk about the physical implementation of these, so now we are either talking about a printed circuit board, where each of these modules or cells will correspond to one chip, VLSI chip, or we can talk of a multi-chip module, where inside the same integrated circuit we have several silicon wafers which are embedded on them and they are interconnected. So, this PCB and MCM are very similar. PCB, the chips are put on a board, MCM they are put on the same package. Similarly, we can have something called system on chip, which is the trend today, where very large systems can be put inside the same chip itself. So, the physical implementation of this high level design can be mapped into either a PCB, MCM or system on chip, SoC. Well, now after this, as we go towards the center, the next natural level of detail that we can go into is the so called register transfer level designs at the level of the behavior. Now, register transfer level designs will look something like this. Suppose R1 assigned R2 plus R3. There can be a number of conditions, if then else kind of a thing. There can be a number of such register transfer operations you define based on the inputs you give. So, here we specify the behavior, but we do not say that how these register banks are implemented, how these adders or subtractors are implemented, how many adders are there. So, all those details we do not specify. But as you can understand, with respect to the algorithm description, as we had said earlier, this is a much more detailed description. Okay. So, with respect to a processor, suppose we are designing a processor, this may correspond to the so called micro instruction level. So, at a very high level you can specify a processor with the external IO pins and the instruction set. But as we go into the design of the control unit of the processor, we will have to specify the different micro instructions, the instruction execution cycle, if there are any pipelines, details of that, what are the control signals, etc. So, these we specify in terms of the register transfer operations. Okay. Now, this register transfer level behavior, when we translate into structure, we get a design where the blocks are registers, multiplexers, ALUs and similar register transfer level components. Similarly, when you map them into the physical implementation, so you can either have an application specific integrated circuit or you can have a prototype on a field programmable gate array. So, it depends on your target implementation, what you are trying to implement or how you are trying to implement. So, as you go into the next lower level or means more detailed level of the design, we get a design which consists of register multiplexers, their interconnections, their control, and at this level possibly we are talking about mapping the design into an ASIC or an FPGA. Okay, fine. But as you detail the design further, from the register transfer level, the next natural jump we take is to have something like a logic level behavioral specification, where if it is a combination logic, we specify the behavior by a set of Boolean expressions, Boolean equations. If it is a sequential logic, we specify by finite state machines. These represent the behavior of the circuit of the system we try to design. Now, as you know, starting from the Boolean expression or FSM, there are many methods which are available for synthesis, where we get a circuit where the basic building blocks now become gates and flip-flops. So, we have now an interconnection of gates and flip-flops starting from the behavior at this level. Now, talking about the physical implementation now at the level of gates and flip-flops, well, normally what happens when you are working through the back-end CAD tool, there is something called a library. It is sometimes also called technology library. Now, in the library you have the standard components already available, standard components like gates, flip-flops, okay, simple arithmetic logic units. So, at this level, once you have the gate level implementation, you simply replace each gate or each flip-flop by the corresponding cell available from the library. So, now at this level, you have actually a tentative layout on silicon where you have the cells. These cells are fairly low level cells, gates and flip-flops, and the way they are interconnected. Okay. So, this is one level of the design, and as you go even further down, you get a design at the lowest level, where with respect to the behavior, see, ultimately we want to implement a circuit typically in CMOS using CMOS technology. So, you can also specify the behavior of a CMOS netlist with respect to the transistor functions. See, transistor functions typically for digital circuits, a transistor or a MOS transistor is modeled in a very ideal way. We treat this as a simple switch. This is the gate, this is the source, and this is the drain. So, if it is an NMOS kind of a transistor, depletion type, if we apply a high voltage to the gate, then this switch is assumed to be turned on, the drain and the source are shorted, but if the gate is at a low voltage, they are turned off. So, each transistor is modeled as a switch. This is what we mean by the transistor functions. So, the whole circuit is modeled with respect to the behavior of the transistors, well with respect to some more simplified model. Now, from the simplified model, when you go to the structure level, we get the actual netlist of transistors which is used to implement the behavior which we specify out here. And finally, at the physical level, we get the actual layout of the transistors. Okay. So, this Y diagram and the way we proceed from the outermost circle to the innermost circle, this tells you the different levels at which we can carry out a design and the three aspects of the design: behavior, structural and physical. Now, one thing I would like to tell, that for a particular design, it is not necessary to go through all the different steps. For instance, if your ultimate target is to build a prototype on FPGA, then you need not go up to possibly the gate level implementation or certainly the transistor level implementation. Slightly higher level implementation can also suffice, provided you have a way to map them into the corresponding FPGA cells or CLBs, whatever you call. Okay, fine. So, to start with, we first talk about the logic design process as part of synthesis. See, we are talking about synthesis, which means we are talking about translating the behavior into the structural specification. So, we start with the level of logic design, where the specification is given either in terms of a set of Boolean expressions, it can be FSMs also, or it can be slightly higher, it can be register transfer level specifications also. So, somehow we are specifying the behavior of the circuit, and from there we are trying to go through the different steps of synthesis. Now, this diagram will show you what are the different steps that we typically go through. Okay. This block, as you can see, logic synthesis, this is the block which accepts the specification as the input and generates some kind of a synthesized netlist as the output. Netlist means some basic components and their interconnection. Now, if the specification is in the terms of Boolean expressions, then this netlist will consist of gates, possibly flip-flops and their interconnections. Well, if it is RTL level, then this netlist may be ALUs, multiplexers, buses and the way they are interconnected. Okay? Fine. So, once you carry out the logic synthesis, you have or you get a netlist where you have much more details about the design. But when you are trying to implement it, this netlist may not be sufficient. Why? See, suppose you are trying to design using FPGA. So, using FPGA you have some constraints. You know that these are the functions I can implement using FPGA and these are the things I cannot. Moreover, let us take another example. Suppose we are trying to design using CMOS. Now, in CMOS again you will be having some kind of a library available with you, where you will be getting a list of available gates or cells which you can use in your design. So, the netlist that you have obtained through the logic synthesis process, the basic cells out there, they will have to be mapped somehow into the cells that belong to that library. So, that process is achieved or accomplished through a step called technology mapping. So, technology mapping takes the netlist which is generated by the logic synthesizer. It also accepts the library. This is a given cell library, okay, and it tries to map the cells out here to the cells available in the library, and as the output it generates another netlist where the basic cells are those which are available in the library. So, this netlist is something which can be implemented. Okay. So, from this you can straight away go to the step of physical design. So, if it is FPGA, you can straight away map this design into the FPGA chip. If you are going for an ASIC design, so this physical design process itself will consist of a number of steps like partitioning, floor planning, routing, clock and power routing, etc. This we will see later. So, this is the essential process, and after completing the physical design, if you find that something is wrong, the circuit is not working according to specification, then you may have to redesign, you may have to go back and change the original specification. Okay? Fine. But as you can see that once you do the synthesis and physical design, well, you have incurred a lot of you can say cost. If it is an ASIC design, you will have to go through the entire steps of the ASIC design process, which is expensive. So, usually what people do before going for the actual physical design, so you take the netlist which was obtained by the synthesizer and try to check whether this netlist is working as per the specifications or not. This you do through a process called logic simulation. So, logic simulation will again take this netlist as the input. Okay. So, it will also take a stimulus which is just a set of inputs. Say I have a circuit, I will say that well I want to test the circuits for these inputs. So, we apply these inputs and the simulator will tell you that for these inputs what will be the outputs. So, I can verify if the outputs are correct or not. So, when you are doing logic simulation, the behavior of all the cells of this netlist must be known. That is available in another library, this is called the component library. Here all the basic components that can be there in this netlist are present, as well as their behavior is also present, which helps in carrying out the logic simulation. So, after simulation we get the performance, and if we see that the performance is not according to our requirement, we again do redesign, go back and change the specs. Now, sometimes even during the physical design we can do something called back annotation. Back annotation means from a very low level design specification we can re-extract possibly the gate level design again. So, we can go back to the logic simulation phase and again simulate with the same stimulus and check the performance. So, if it again see if we again find that it is not matching, we can again go back and make changes. So, mismatch in performance may need to changes out here, may need to some changes in the parameters that we use during logic synthesis. Well, of course, there is another step involved which is slightly beyond the scope of the present discussion. This is called logic verification. See, logic verification is a process which accepts the specification and tries to formally verify whether the specification is correct or not. Okay, but this is a block which we would not be discussing much during the course of the present class. Okay. So, now let us see some of the blocks out here, what are the basic responsibilities and basic tasks of this. We start with the block logic simulation. So, as we had mentioned, the logic simulation process takes as input a logic level netlist. Logic level netlist means a netlist comprising of gates, comprising of flip flops, and it simulates the functional behavior. Functional behavior means most commonly we would like to see whether the input output specifications are correct, that if we give a particular input to the circuit, what is the expected response or what is the response that we get. And this logic simulation tool is a software program where the circuit you want to simulate is modeled in terms of a suitable data structure, and through a systematic scan of the circuit of the data structure we carry out or we evaluate the values of the gates, and finally we obtain the values of the output. And this netlist which is taken as input, this if you recall, this is a netlist which is obtained through a process called synthesis. Well, sometimes we can also get the netlist through a process called schematic capture. Now, schematic capture is an option which is available in many CAD tools. Just let me try to explain what this schematic capture is. Schematic capture is an interactive way to specify a netlist. See, if you look at the typical window of your CAD tool, you will find typically that on the left pane you will be having a number of symbols available with you. The symbols may be the symbols of the gates, okay, etc. So, what you can do using mouse, you can select this and you can drag and drop, you can draw a diagram here. For example, you can put an AND gate out here, you can put an AND gate out here, you can put an OR gate out here, okay. And then using mouse again you can click here and click here, these 2 points will get interconnected, okay. These 2 points will get interconnected, these 2 points will get interconnected, okay. So, in this way interactively using a graphical user interface and mouse you can draw a schematic diagram. So, when you complete the drawing of a schematic diagram, this is nothing but a netlist which you have created, okay. So, your input can also come from this schematic capture process. But when you are doing simulation, you need the behavior of the components. Behavior of the components, what does this mean? Suppose if the components are simple gates like AND or NOT, then what you need is the input output behavior of the gates. You need either the Boolean function or the truth table in some form. So, you need the behavior of the gate in order to evaluate the output of a gate when some particular input values are applied to it, okay. So, behavior of the components are assumed to be present in the so called component library. Now, component library can be quite exhaustive. You can have gates out there, you can have sequential elements like flip flops and registers, you can have slightly more complex combinational blocks like multiplexers, adders and other functional modules like decoders, etc. Now, logic simulation is used before we are actually going to the physical design. So, one of the requirements of logic simulation is that it should be possible to handle large circuits. So, when we talk about large circuits in the present day scenario, we are actually talking about millions of gates, okay. So, the logic simulation process should be very efficient, it should be able to handle large circuits of the order of millions, it should be relatively fast, and in order to handle so big circuits fast, typically some special hardware called hardware accelerators are used, whose sole objective is to speed up the process of simulation. It acts just as a helper or a coprocessor to the software simulator. Using that hardware accelerator, you can actually speed up the rate at which you can process and simulate the gates, okay, fine. Now, this is what simulation is. Now, when you talk about the simulation objectives, okay. So, the main objective is of course to verify the functional correctness. Functional correctness, how do we verify? We verify it like this. Given a circuit, so I am treating it as a block diagram, this is some kind of a netlist, there are some inputs, there are some outputs. So, through simulation I can apply a set of inputs to it. Suppose this is an adder, okay. So, I specify a set of input data and I check whether the output result is coming as per the specification. If it is an adder, I know that what is the expected output, okay. For given inputs, I can verify what outputs are obtained and what output should have been obtained. So, this requires, as I said, application of a set of test vectors. Now, we have already seen during our discussion of the language Verilog that we can specify test benches using Verilog, which is used for the purpose of simulation for specifying the test vectors that we apply to a given module. So, functional correctness is of course one of the main objectives, but in addition to functional correctness, we need something more. We need something called timing analysis. Like if we have some estimate of the delays of the basic components, say gates, then you can estimate that what is the total delay of the circuit, what is the maximum speed with which our circuit can work. We can identify the critical paths in the circuit. Critical paths are those paths which actually affect directly the total delay. So if we can optimize the critical path, the total delay of the circuit will become less. So through timing we can analyze potential problems like hazards, races, and if we see that there are some problems, we can go back and redesign and again do a timing analysis to find out that whether these problems get eliminated or not. So timing analysis, although it may look to be a slightly more complex process, yes, it is a more complex process, but for big and complex designs it is an essential part of the design process. See, you do function simulation, you see that the input output behavior is correct, but that does not tell you anything, that any practical design will have the design requirements. You will have some constraint on the speed with which the circuit is supposed to work. So through timing simulation only you can get an estimate about the actual speed with which your circuit will be able to work or operate. Okay, fine. Thirdly, there is another simulation objective which is also a very important process. This is something called test generation. See, test generation is something which is required for manufacture test. Well, what is manufacture test? See, you have a design and you have done some kind of synthesis on it. So what you have obtained is a net list. Okay? So this net list is available to you, but this is not something which you have already fabricated. This net list is still on your computer. Okay? So through simulation you try to verify whether the net list is working as per the specification. Okay? This is done on the design, but suppose the design process is through, you have completed the physical design process also and now the chips are getting fabricated. Suppose you have fabricated 1000 chips for your design. Now during fabrication there can be a large number of faults which can creep in, obviously. So once you have manufactured the circuit in terms of the chips, you will have to test each and every chip by applying some input stimulus, input test vector and checking the output. This is the so called manufacture test that I am talking about. So in this step, well, again you will have to apply some input test patterns, but here again we do some kind of a modeling. We assume that what kind of faults can potentially occur in the circuit, and with respect to that assumption we try to obtain a set of test generation. Because see, suppose I have designed a processor and I ask you that what are the inputs I should apply to this chip in order to verify that this chip is working correctly before I can actually send this chip into the market for sale. Now it is a very difficult question, obviously. You will have to tell that, well, these are the testing or these are the tests I need to apply to the chip. So in order to do that, you will have to identify or understand that what kind of defect or fault modeling you are doing and whether the test vectors or the test set you are trying to apply will be able to detect all the modeled so called faults under your consideration. Okay? So this is also a complex problem. Okay. So after simulation comes the process of synthesis. So now let us see what this logic synthesis process is all about. Now Logic synthesis process with respect to the Y diagram I have already mentioned. Well, with respect to the behavior, you have Boolean equations and finite state machines. From there, you want to carry out a translation into the structural domain where your basic components will be gates and flip-flops. Okay. Now you must be familiar with a number of methods that are used to translate from a Boolean equation, an FSM, into a netlist of gates and flip-flops. You have Carnot map methods, you have Quinn-McCluskey methods, you have formal ways, formal tabular ways to synthesize an FSM. And when you are synthesizing an FSM, you know that typically you separate out the combinational part and the sequential part and you synthesize them separately. Okay. So, there are standard methods of doing them, but we will see shortly that the standard methods have some problems. So, we need to do something about it. So, as I said, typically for sequential circuits, the combinational parts and the sequential parts are handled separately. Okay. Now, when you are carrying out logic synthesis, depending on your requirement, depending on your ultimate goal, your objective may vary. Suppose you are trying to design a circuit for a very critical application where delay is most important to you. You want to design a circuit that will work as fast as possible. So, here, well, if it is combination circuit, your design goal will be to minimize the number of gate levels. So, as you reduce the number of levels, the total delay of the circuit will also reduce. Well, another alternate design goal may be that, well, I am not that much interested in delay, but I am more worried about area. So, I want to design my circuit within the smallest area possible. So, there, well, our requirement translates into minimization of the number of gates. Well, we are not worried if the number of levels go up, but we are more worried of the number of gates. Thirdly, there is another very important design goal which has crept up in recent years with the proliferation of you can say mobile and handheld devices which operate on mostly on not on electric mains power, but on backup battery power. So, one objective in the design of those circuits is that if the circuits involved in the design consume less power, we can run them for longer periods of time, and that is certainly very desirable. So, we want to minimize signal active. Signal activity means as the switching activity in the circuits get reduced, the total power consumption also get reduced. So, we want to ensure that the number of signal transitions that are going on, signal transition means 1 to 0, 0 to 1, they are going on per unit time in the circuit is as less as possible. So, these are the three conflicting design requirements. See, well, you typically these three design goals are mutually conflicting. So, if you try to minimize number of levels, you may see that the area is going up, and if you want to minimize area, you may say delay may go up. Power, again the same thing holds for power. So, it is very difficult to consider all these three things at the same time and try to do the synthesis. So, typically people will give priority to one of these and then go ahead with the synthesis process. Not only that, when you are doing synthesis, you have some other external constraints that will guide you, like some typical constraints may be, well, you will have to synthesize only using NAND and NOT gates, or maybe NOR. This is the so called target library. So, you will have to complete the synthesis where the components belong only to the target library. These are the typical constraints that you will have to satisfy. Now, there are some other considerations that when you are doing synthesis, obviously today we want to handle very large circuits. So, we would like that we should be able to handle fairly large circuits within a reasonable amount of time. But unfortunately, the problem of getting the best solution has been proved to be an NP complete one, which means that it is computationally infeasible or computationally very expensive to ensure that the design you have synthesized is the best possible one. So, obtaining the best possible design is not practical for large circuit. This is something which we need to understand. Moreover, as we have just mentioned, that we may have mutually conflicting requirements. Some designer may say that, well, we want to concentrate both on reduction of area and delay, but these two may be mutually conflicting. So, actually how do you do this? See, this logic synthesis process is typically a fully automated process. This is a well understood, well studied process, and we do not need or we do not require any user intervention in between. Okay. And there are some other things that you will also have to look at, some considerations which are dependent on target technology. First one, of course, I have just mentioned that you will have to use gates only available in the library. Okay. So, maybe you are using an exclusive NOR gate which is not in the library, but ultimately you will have to break up that exclusive NOR gate into a netlist of NAND gates. That will really not help your cause. Okay. Maybe your delay will go up. So, it is better if you know what are the gates that are available in the library and you carry out the design based on that. Okay. Now, another example which has been mentioned here is that if you have a gate with large number of inputs, you better break it up into smaller gates. Well, what I am saying is that suppose you have, say, an AND gate, let me call it. So, you have an AND gate with a large number of inputs. So, what I say that instead of having one AND gate with a large number of inputs, you may possibly break it up into several smaller AND gates. But you may argue that, well, if I do this, I am increasing the number of levels. Okay. So, apparently I am also increasing the delay because the number of gate delay is more, but well, this is not true. This is not true. Why? Because you try to understand that gates are typically implemented today on chips using MOS technology, typically CMOS. See, if you look at a NAND gate, the way a NAND gate is constructed in CMOS, see, in the pull up you have a set of P type transistors, and in the pull down you have a set of N type transistors in series. Well, now as you increase the number of transistors in series, the total impedance of this chain of transistor increases. So, when the output of this gate tries to switch from 0 to 1, actually you are either discharging a current along this path or you are charging a current from this path, because the load can be approximated by a capacitor. So, either you are charging the capacitor or you are discharging the capacitor. Now, if you have many transistors in series, the time it will take to discharge the capacitor will be much larger. So, larger the number of inputs, slower will be the gate. So, it has been found out that rather if you break it up into smaller input gates with a larger number of levels, maybe this will be a faster solution as compared to this. Typically, we do not use gates whose inputs are more than 4 or 5. That is a rule of thumb. Okay, fine. Okay. So, there is another step called technology mapping that I had mentioned, that technology mapping is a process where we have a netlist with us, we have a technology library with us, we will have to map our netlist from some modules which are available in the technology library. So, the basic concept is that during synthesis we will have to map portions of the netlist to so called cells which are available in the cell library. See, cells can be the standard gates NAND, NOR, NOT, AND or invert, or depending on the target where you want to map the design onto. If it is FPGA, so you can have FPGA cells, you can have standard cells where you have standard basic building block like adders, multiplexers, decoders, etc. So, actually what I was saying is that is something like this. Say you have a given netlist to start with. This can be a netlist of gates, any kind of big netlist you have obtained. Okay. So, it is a big netlist you have obtained. I am showing a part of it. Now, you have with you a technology library. Now, the technology library you will be having small netlist. You will be having netlist 1, netlist 2, etc. Netlist, what this netlist will contain? Say it will contain something like this, that if we have something like this, this is equivalent to what? This is A and B, this is A bar, this is B bar, and the output will be this is A or B. Okay. So, if you have a sub-circuit like this, this is equivalent to a OR gate. So, you will have to find out this kind of sub-circuits in the original circuit, and you have to identify that which small netlist out here matches with that, and you can replace it by the corresponding gate in the technology library. So, actually what we will have is that you will be dividing the total netlist into smaller mod, maybe this will be one module, there can be overlap also, this can be one module. So, ultimately this segment will get mapped into one particular component of the technology library. Similarly, this segment will get mapped into another component from the technology library. So, in this way you can map the different sub-circuits. Of course, this is a graph theoretic problem, you can understand. You will have to match the sub-circuits in a graph and you will have to find out. So, objective is obviously to minimize ADR delay power. There can be conflicting requirements, should be fast, it should be able to handle large circuits, and typically technology libraries are large. So, I have another example to show you. So, suppose you have obtained a sub-circuit like this as part of the bigger circuit. Now, you search the technology library and find out that, well, there you have an information that if we have a sub-circuit like this, this is equivalent to a component. This is AND or invert. This is an AND or invert gate. So, AND or invert gate is available as a component in the technology library. Okay. So, the idea is simple. You have a big netlist of gates, you try to find out the small subcircuits from there which matches with some netlist available in your technology library, and if you find a match, replace it by the corresponding component of the technology library. So, if you do this, what you have is that your entire netlist which was there at the at the beginning will now get transformed into a netlist of cells which have been picked up from the technology library. Now, as I said, there can be overlap among the cells. The objective is to have minimum number of cells if area is important, or to reduce the number of levels of the cell netlist if delay is more important, and so on. Okay. And with respect to the diagram, so last for the logic verification, which I had said that well, you do this logic verification in order to check whether a given specification is correct or not. To verify that this synthesized netlist, well, it is not always the netlist, sometimes this can also be the behavior. Okay. So, it is not necessary that you are verifying always on a given netlist, you can also verify on the behavior. The objective of doing this is to detect design errors. If I have made some error while coding the design, and if we are trying to verify the netlist, then we are also trying to detect if there are any synthesis errors. Maybe there are any problem with the synthesis tool. So, I want to check whether the synthesized netlist is also correct. Basic objective is to ensure functional correctness. During logic verification, we are not talking about delay or power, we are basically talking about the input output behavioral specification, whether they work correctly. Well, we talked about simulation. Now, actually simulation is also a way of doing logic verification, because there also we have a given netlist, we apply some inputs and we check the outputs. So, logic verification broadly falls under two categories. One is simulation, which is done on a computer typically by modeling the circuit in some way. This is typically very fast, where you can simulate circuits which are very large, so that means up to of the order of million gates also. It can handle very large circuits, but in simulation the only problem is that you have to clearly specify that these are the inputs I need to apply and I want to check the output for this. Now, the question arises that how many inputs you need to apply before you can say with confidence that, well, I have verified my design. Now, it is naturally a very difficult question, particularly if your design is complex, like a processor say, so that you are designing a CPU. But in contrast, the other method, which is called formal verification, this does not apply any input vector, rather it tries to prove that your circuit behavior is correct through formal techniques, through mathematical techniques. And since it uses mathematical techniques, it is much slow, but it is an exhaustive method. Exhaustive in the sense that it will take care of all kinds of errors which are there. So it is not just dependent on what are the inputs you are applying, and since it is slow, you can apply it only for smaller circuits. So today actually we had looked at the different aspects of logic synthesis, logic simulation, technology mapping, logic verification. Now, in the next class we will be looking at some of these steps in more detail. Okay, we will be looking particularly at this step of at the process of synthesis, both at the level of logic, and subsequently we will see that when we have a design at a higher level, what do you do about it, how do you synthesize a design at the behavior level also.